Okay, so now some applications of the scientific notation, which is where I'll show you how to do this mess in Desmos. So a typical MP3 file fills about 4.4 times 10 to the 6 bytes of disk space. Question is, how many average songs can my iPod Classic, which has 80 gigabytes of disk space, hold? Note each gigabyte is 1 times 10 to the 9 bytes. Okay, so first off, we need to know how much space does this thing hold? Well, I know if I multiply 80 times this 1.1 times 10 to the 9th, this is the total number of bytes on our iPod Classic. And if I want the average amount, I'm going to divide by 4 times 10 to the 6th. Well, multiplication here, we can multiply this number not in scientific notation times the number in scientific notation and still get 80 times 10 to the 9th. This is technically not scientific notation because this should be 8, which if we wanted to convert that to scientific notation, we'd make it 8 times 10 to the 10th. But we don't really need to worry about that. If you want to be able to do this by hand, you can divide the numbers and you can divide the times 10s by each other. So 80 divided by 4 is 20. And then 10 to the 9th divided by 10 to the 6th. If anyone remembers your algebra classes, the rules of exponents, when you have the same base, you subtract the exponents. So this is really times 10 to the 3rd songs is what we end up with, which if we want that in decimal notation, we'd say 20,000 songs can be held on his iPod Classic. Well, let's do this calculation in Desmos. I'm just going to type this whole thing in Desmos and let you see how Desmos fills that out. So I'm going to do 80, and I'll put parentheses around it, and then 1. And so how you type in times 10 in the calculator is you use the multiplication button, not the letter X, and then 10 exponent 9. Okay, so there, notice how Desmos automatically puts that in scientific notation, 8 times 10 to the 10th. And then I want to divide that entire mess. So I need parentheses around the whole thing, do division, by 4 times 10 to the 6th. And here's our answer. So Desmos just spits out the whole thing in decimal notation. Okay, well, let's now look at Newton's law of universal gravitation. Just as a reminder, this formula is the force equals the gravitational constant times the mass of the first object times the mass of the second object divided by the radius squared. In other words, the distance between the two. So we're going to use Newton's law of universal gravitation to find the gravitational force between the Earth and the Sun. All right, so we're given everything here. We just have to plug it into the formula, and boy, is it annoying. So we got 6.674 times 10 to the negative 11th. That's the G. And then the distance from the Earth to the Sun is 1.496 times 10 to the 11th meters. So I'm going to put 1.496 times 10 to the 11th in the denominator, and we need that whole thing squared. The mass of the Earth is this number of kilograms, so 5.974 times 10 to the 24th kilograms, and the mass of the Sun is 1.989 times 10 to the 30th kilograms. Notice these are the numbers that were given to us on the previous page, right at the beginning, not in decimal form. Okay, I'm not going to try to do this by hand. I'm just going to jump straight to Desmos and type that whole thing in. So one of the advantages of Desmos is you can see what you're typing in to note if you've made a mistake. So here comes negative 11. So there's our first value. I'm going to use parentheses for each one of these scientific numbers, even though they're not actually necessary. So 5.974 times 10 to the 24th. Oops, I didn't need that in the exponent. And the last one, now notice I haven't done the division yet, and we can see that the product of all those numbers is 7.9 times 10 to the 44th. Okay, so now we need to divide this whole thing by the distance between them. So that was 1.496 times 10 to the 11th. And remember, we need to square this amount. So that's why I have parentheses around that number, and then I'm just going to use the exponent. I'll click this one, and we want it squared. And there's our result. So, boy, I guess we'll write the whole thing. 3.54334231375 times 10 to the 22nd. And our author kindly points out what the units are on this. It's kilogram meter per second squared. Kilogram meter per second squared. We can check that with dimensional analysis um, by looking at the units on these things. Um, so, ooh, so I got this wrong. It's kilogram meter per second, all of that squared. So if you look, this was kilograms. This is kilograms. So kilograms times kilograms is our kilograms squared. And then this 1.49 is our meters. So there's meters squared. So we'll have to figure out what the units are on this G. And I believe that's meters per second squared. And so, boy, that's where we'd end up with the units. But you know what? We're going to skip figuring that out.